Cool. Yeah. So, okay, so maybe I'll just start by talking for a few minutes about the project. So I'll basically just repeat things that I already said in the past, but I'll just sort of reiterate them. So the project is very open-ended, and there are several options for stuff you could do it on. It could be taking one of the results that we covered in class, but we didn't go too much in depth into, and just read the relevant papers and write like more in detail summary of something like that. It could be like a new topic that we haven't covered in class, some application, for example, like to quantum codes or property testing or PCPs or anything like that that you want to cover, that you're interested in. And again, read the papers and then cover that. It could be more broad, could be more in depth, very, very much open-ended. One thing I ask is that just shoot me and Max an email once you have a topic, just so that we know what your topic is and we just sort of approve it. That seems reasonable. And anything that sort of is even vaguely related to the HDX and expander should be okay. But just shoot us an email before you start working with the project. What else? I guess I consider deadline. I mean, there's no real restriction on the deadline, but I don't want to drag for too long. So let's just to be fair, set the deadline to be maybe the first day of the or maybe like 2 weeks after the end of the quarter. And if for some reason you find that you need more time because you're doing something that's like more in depth, then it's fine. You can extend it longer. Basically, you'll get your grade only after you submit your final project. So it is something up to you. Yeah, I don't know. Any questions on that? Yeah, and again, and if you're not sure, I mean, one suggestion is just come to either office hours and mine or Max's and just talk about it with us. If you have some ideas, and we can try to help you out. Or shoot us an email, or we can discuss it on Piazza. I mean, either way is fine. And again, the whole goal is that you find that topic you're excited about and that is related to this class, and that you spend the time studying it and then writing a survey or summary, sorry. And like the scope should be maybe like 6 to 10 pages. I mean, that's like a reasonable length. So don't make it like a 50-page thing, because then we need to read it, and sort of that's not the goal. I mean, but if you're interested in research, this could be like a good starting point for you to sort of do some literature stuff survey before you start doing research in some area related to the topics covered here. So this could serve both a good starting point for you and also as a final project for this class. Yeah. Next, do you have anything to add?
Nope, that sounds right to me.
Perfect. So I'll add this language to the website and also post about it in Piazza. Yeah, but basically just let us know what you're interested in, and then we'll basically approve everything. And again, also remember you can do it individually or in pairs. I mean, both options are fine. So okay, yeah, that's it. So
okay.
Floor is yours, Max.
Yeah, looks like we're already recording. So let me share screen. Okay, here we go. So we're going to briefly review a little bit about what we talked about last time. I'm going to go fully back over the definitions, I think, of the averaging operators, because we'll be using those a lot, and they're an important definition. But first, let's just recall a little bit what we talked about last time. So we mostly talked about kind of a new way of defining an equivalent way on graphs of defining two-sided spectral expansion that we called random walk expansion. And how is this defined? It was we kind of looked at the difference between the non-lazy upper walk and the lower walk. So the definition was given, technically we only did this for deregular graphs, but really it works for any graph. It doesn't have to be regular. So given a graph G, B, E, we say G is a gamma random walk expander if the spectral norms, the largest eigenvalue and absolute value of the non-lazy upper walk, also called the adjacency matrix when you're on a graph, the normalized adjacency matrix, minus the lower walk, u0 d1, which we'll call is also equal to 1 over n times j on a graph, if this is less than or equal to gamma. So that was our definition, and we observed observation. We observed that this was exactly equivalent to two-sided spectral expansion on a graph. So G is a gamma random walk expander if and only if G is a two-sided gamma spectral expander. Okay, and then so what else did we do? Well, we didn't quite yet get to the point where we could define the generalization onto complexes, but I did kind of go through some informal and more intuitive kind of pictorial representations of how we extend these, not the non-lazy upper walk, or I guess I just talked about so far the upper and lower walks, to complexes, right? We saw these kind of diagram pictures, Hasse diagrams that represent complexes. And we saw that kind of there were ways to extend the upper walk, the node edge node walk, up to higher levels of the complex, right? We could start at an edge and then walk up to triangles and then walk back down to edges, or from triangles to pyramids to triangles. And these were kind of the generalized versions of the upper walk. And you could also do the lower walk. So you could do triangle to edge to triangle. That would be the lower walk at level 3. So we kind of gave this informal intuition. And then I started actually going into formal definitions about the averaging operators, and I hadn't quite hit kind of defining the higher order random walks, but it's kind of no surprise that they're defined analogously. They're just compositions of these operators. Since the operators are a little bit complicated and we'll be using them pretty heavily in the rest of the course, I'm going to go through the definitions of those again to make sure that everybody's comfortable with them, and we'll discuss a little bit again what's going on with those definitions. So let's go ahead and review that. So the averaging operators. So as a reminder, and I made this point last time as well, but a reminder that in X pi is a joint distribution. So pi, maybe I should say, equals pi 0 through pi d is a joint distribution over chains of faces, one from each level of the complex. And the way this joint distribution is generated is that a d face is drawn from pi d, and pi d is some arbitrary distribution. And then each lower level is then picked uniformly at random from the initial d face that you drew from pi d. That's how this joint distribution is defined. And we talked a little bit about how it's useful to work over the joint distribution instead of the marginals, right? And previously in the class, when Shahar was doing Oppenheim's theorem, we tended to work just with the marginals, with pi I. But when you want to talk about kind of relationships and conditional probabilities between levels, it can be useful to talk about the joint distribution. For instance, something that we'll see very soon is you might want to kind of look at the difference between these two processes where you're at levels kind of k and k plus 1. Let's say that we sample a k plus 1 face from the marginal at k plus 1, and then we sample a k face conditional on that k plus 1 face. Because of the joint distribution, so this is the same process as just sampling a joint pair from levels k plus 1 and k. And we'll see it's useful to be able to compare this to the process of, say, drawing a k face from the marginal and then a k plus 1 face conditional on that k face. That's also the joint distribution over pairs in k and k plus 1. So we're going to see that this is useful to kind of, we're able to more easily move around the complex. We can draw a k face and then conditionally a k plus 1, or a k plus 1 and conditionally a k. We know those are the same process when we work over the joint distribution because they're both just given by the joint distribution. Anyway, this is a little bit vague at the moment, but we'll make it very explicit when we do our first kind of definition.
One thing.
Yeah.
So here's maybe another way of viewing this joint process that might be useful. So you can imagine that you're sampling some d face from pi d, and then you randomly choose like an ordering of all the elements in it. There's d elements in it, and then just remove them one by one based on this order. And this gives like sigma d minus 1, sigma d minus 2, and so on. Just remove elements one by one. Basically, or equivalently, every time you just, to go from a k face to k minus 1 face, you just remove one of its elements randomly in the formula.
Right. This is actually a view that will be useful, although perhaps not today, but in Tuesday's lecture. Yeah, we'll see. It's equivalent. Picking a random k face from a k plus 1 face is equivalent to just removing one random element. Those are the same process. Yeah, so you can always just remove an element uniformly at random to move down as well. Yeah, good point. Okay, so let's remember the definition, of the averaging operators, which apparently cannot spell. Okay, so there are two averaging operators, kind of on each level, more or less. There's the up operator and the down operator. So what is the up operator? The up operator lifts functions from ck to ck plus 1 by averaging downwards. And what do I mean by that? Well, let's take a look at what it looks like here. So uk takes in a function on k faces, so f lies in ck, and lifts it to k plus 1. So its input is going to be a k plus 1 face. So we have tau, which lies in xk plus 1. And what is this equal to? Well, we're going to define it. We're going to see two ways of defining it. The first is going to be in terms of the joint distribution. So it'll be kind of the joint expectation of f. So f is a function over level k, right? So f needs to take in the k face, f of sigma k, given that sigma k plus 1, so conditional on the fact that the k plus 1 face in the chain is equal to tau. So let's maybe actually take the diagram view. So remember that we kind of had this way of writing complexes through stacking up the levels of the complex in a diagram that we call the Hasse diagram. So let's take a look at what does this look like in the diagram view, kind of recalling back to our informal explanation. Well, we'll fix a k plus 1 face tau, and then all we're doing, remember then kind of picking sigma k, what we do is we pick it by randomly removing an element from tau, or equivalently picking a sub k face uniformly at random. So we just look down in the complex at everything that contains tau. So these are all kind of the things that contain tau, and we're just going to average uniformly at random over them. That's all that this conditional expectation is saying. It's just a nice way to write this. But informally, kind of this is all that's going on. You're fixing something a level above, and you're still just averaging down. So to write this out explicitly, because the average is uniform and there are k plus 1 sub k faces, this is 1 over k plus 1. So here's the explicit or closed form of the expectation. Then we sum over sigma contained in tau, where the size of sigma is equal to k of f of sigma. So in this case, it really is just the uniform average down in this diagram. So the up operator is the simple one, because when we move down in the way that we defined our joint distribution, all we're doing is uniformly removing a vertex at random. Okay, so the second operator is the down operator. The down operator, let's do it at level k plus 1. It lowers a function on k plus 1 faces to a function on k faces. So ck plus 1 gets mapped to ck. So let's take a look. Let's take a look at dk plus 1 f. So now f is a function on ck plus 1. And we'll look at tau. Tau now lies in xk, right? So because dk plus 1 is lowering down to functions on k faces, so it takes in a k face, tau. And we're going to do the same, a very similar definition with the joint distribution. In fact, one of the benefits of using the joint distribution is you can really see kind of the similarity between the up and down operators. So they're going to look a lot more similar than when you write out the explicit form, which is a little bit more complicated. But this similarity will be very useful in the next kind of proposition that we prove about the up and down operators. So this is also just the joint expectation, but it's the opposite direction, right? So it'll be the joint expectation f of sigma k plus 1, given that sigma k is equal to, let's rewrite that, sigma k is equal to tau. So let's look at our diagram again, where this is level xk. And let's say here's tau. Here's xk plus 1. So what are we doing now? Well, now we're looking up in the diagram. And we're looking at all of the k plus 1 faces that contain tau. So what is this? This is basically the link, more or less, abusing notation slightly. This is more or less the link of tau at level k plus 1. It's everything that contains tau at level k plus 1. And the distribution now is a little bit different, right? Because when we move up the complex, we have to use kind of these conditional distributions. We have to be a little bit more careful. So instead of being uniformly distributed, like when we move down up here, it's now distributed. These sigmas are now distributed as if they're on the link of tau. And so what does that mean for writing out the closed form? Well, it's a little bit more complicated. This is equal to, there's a normalization for being in the link of tau, which is pi k plus 1 of x tau, kind of the k plus 1 weight of tau. And then we just sum, then it's pretty similar, right? Then we just sum over sigma now that contain tau, where sigma is of size k plus 1. And then we just take the marginal over level k plus 1 of sigma and f of sigma. So there's the closed form for D and U. Okay, so this is, I think, where we stopped last time. So are there any questions about anything we did last time or about these? So these definitions will be fairly crucial for us. Please ask if there's any useful clarification. I think like for working through kind of theorems, it's definitely good to be able to use and be familiar with these definitions. But when you're just kind of informally thinking about the operators, I always think it's good to think about this diagram viewpoint. Like intuitively, all that's going on is these diagrams. But formally, maybe you have to make sure things are weighted correctly. Really, all that's going on in these definitions is you're just making sure things are weighted correctly. But informally, always think about the diagrams. At least that's what I do. Yeah, okay. I'll pause to see if there are any questions before moving on. Okay, if not, let's go ahead and prove kind of our first fact about the down and up operators generalized to simplicial complexes. So remember back when we defined the down and up operators on graphs, we saw this interesting relation that they were basically, in the standard basis, they were basically transposes of each other. Up to, I think one of them was like 1/2 and one of them was 1 over D. But up to scaling, they were basically transposes of each other. And in fact, this is a kind of an example of a much more general phenomenon, which is that when you kind of correctly scale things and define stuff with respect to the correct inner product, in particular the inner product we normally use, that's with respect to the distribution pi, you'll actually get that these are adjoint operators. So claim the up operator and the down operator are adjoints. And I'll remind you what this means. Are adjoint operators. So what does this mean? And also, I'm referring to the inner product that we've been using, like I was saying, with respect to the distribution pi. So what does this mean? This means for all f in ck and for all g in ck plus 1, we have the following. uk applied to f of g is equal to f of dk plus 1 g. So you can flip it in the inner product and you'll move between the up and down operators. So this is like a generalization. So when you have a normal kind of non-weighted inner product, transpose, like adjoints are transposes. So when you move to weighted inner products, things are a little bit different. It's not just a transpose, but you get this general result because of these are inner products over pi. You get this general result that they're adjoints.
Max, maybe it's worth pointing out that these inner products actually live in different spaces.
Sure.
So you can say yeah.
Yeah. So this is a kind of a subtle point that this this inner product, so UKF and G are both functions in CK plus 1. So this inner product, there's actually kind of a sequence of inner products and a sequence of spaces, right? So there's an inner product over each CI space. And this is the inner product that's over K plus 1 faces. But then over here, F is just in CK, right? And DK plus 1G is also in CK. So this is an inner product over XK, over K faces. Well, really over CK. But so you can still define adjoints if you have kind of a sequence of spaces and operators mapping between them, right? U and D map between CK and CK plus 1 and CK plus 1 and CK. So when you define a jointness, you actually move between the corresponding inner products on these two spaces. Yeah, Shahar, I don't know if you have anything you wanted to add to that.
I mean, it's a subtle point, but somehow, when we write inner products and we don't write a domain, it might seem like, within the same domain, but actually these objects live in different domains.
Yeah.
So I think it is useful to observe that.
Yeah.
And
yeah.
Somehow, the reason this is true is exactly because of the way we defined the up and down operator with respect to the conditional pies, and why, and the inner products on CK plus 1 are different as pi k plus 1. This fact exactly makes a matchup. That's the reason for the matchup.
Right. Yeah. So we'll basically see that these will match up because of exactly this thing that we were talking about earlier, where one of them will kind of be we draw a K face and then we draw a K plus 1 face conditional on the K face. The other will be we draw a K plus 1 face and then a K face conditional on the K plus 1 face. But both of these are just the joint distribution over K and K plus 1 faces. And so kind of the way we define things work out really nicely. And I'm about to explicitly write this out. So hopefully it'll become a little bit more clear. So what's the proof of this? Well, it's basically exactly what I just said, but let's actually go over it fully formally. So we'll show the following. So we'll show that UKFG. So for simplicity, I'm not going to write which inner product I'm in every time I draw an inner product. But know that sometimes the inner products, like when I flip, are indeed over kind of CK plus 1 or CK. It's kind of in the background. You should know it, but you don't have to worry about it that much because we've defined things such that it's always going to work out. So we'll prove that UKFG is equal to G DK plus 1F, and that both of these are in fact just the joint expectation over chains.
I think you flipped F and G in the second expression.
I definitely did. Thank you. Yeah, G and F should not move sides, just the operator. Thanks. F of sigma K, G of sigma K plus 1. So this is the joint, just the joint, F times G jointly over pairs from the joint distribution of a K face and a K plus 1 face. Okay, so let's formally prove this. Okay, so let's first look at the up operator. So we have UKFG, and just by definition of the inner product, let's write this out. So this is equal to what? Well, okay, so here's actually where we do kind of need to know that the inner products are at a different level, that this one's actually at level K plus 1. So when we write this out, what is this? Well, this is a sum over K plus 1 faces, right? Tau and XK plus 1 of what? Well, by definition, it's the K plus first marginal of tau. And I'm going to just move G of tau first. Doesn't matter whether I multiply by G or UKF first. So G of tau, UKF of tau. So this is just the definition of the inner product. I haven't done anything interesting here yet. And let's now substitute in the definition of UKF, the joint expectation definition. So this is now equal to the sum where most of the things are the same. G tau, but now I'm going to plug in this expectation. So this is the joint expectation of what? It's F sigma K, given that sigma K plus 1 is equal to tau. And I now argue that we're basically actually done. And why is that? Well, let's look at kind of how G and F here are jointly distributed, the k+1 face and the k face that we get. What have we done here in this sum? Well, we're first we're sampling a k+1 face from the marginal, right? We're sampling a k+1 face from pi k+1. Then second, we're sampling a k face from the conditional distribution on k faces given this tau that we've sampled from k+1. So what we've done is, looking at the pair, what we've done is we've sampled from the marginal at level k+1, and then we've sampled a k face conditional on what we sampled from the marginal. But by kind of joint laws of probability, this is exactly just a jointly distributed pair over sigma k and sigma k+1, right? So I claim this is exactly a jointly distributed pair. And so we could just look then at the expectation over the joint distribution of, I guess in this case, G of sigma k+1. We draw the k+1 face, and then we draw the k face, F of sigma k. So the point is, in this version, we kind of draw tau from pi k+1, then you draw the k face sigma from kind of xk conditioned on the fact that we drew tau from pi k+1. And this is the same as drawing from the joint distribution. So we just get this expectation over the joint distribution. Okay, let's see the argument for the down operator. It's basically exactly the same. It's just going to go the other direction. So F dk+1 G, what is this equal to? Well, now we're over k faces, right? So F dk+1 G, this is an inner product over ck, over k faces of the complex. So this is now the sum over tau in xk. Now we're going to draw from the marginal at level k, right? This will be pi k of tau, f of tau. And then we'll have dk+1 G, but for simplicity, I'm just going to already substitute in the conditional or the joint expectation definition, right? So dk+1 G is equal to what? It's equal to the joint expectation of G of sigma k+1, given that sigma k is equal to tau. And now by the exact same argument, except flipped, we're done, right? Because now what are we doing? Well, we're now drawing a k face first from the marginal at level k, and then we're drawing a k+1 face conditional on having drawn that k face from the marginal. So drawing a k face from the marginal and drawing a conditional k+1 face, that's still just drawing a joint pair. That's still distributed like the joint distribution on sigma k and sigma k+1. So again, it doesn't matter which direction we've approached it from. Either way we approach it, it's still just the joint distribution. So we can still write this. Oh, red still. We can still write this as the joint expectation. This time maybe f comes first, but it doesn't really matter. F of sigma k, G of sigma k+1 over the joint distribution. And of course, the product in here is commutative, so these are both the same. And we get the desired result. So we've seen that the up and down operator are really just approaching, at least within kind of an inner product, are really just both ways of sampling things from the joint distribution, of sampling something from level k and level k+1 jointly. If you want to go, start at level k and go to k+1, then you use the down operator. If you want to start at level k+1 and go to level k, then you use the up operator in terms of inside the inner product. But they're really just the same thing by how we've defined them. Okay, any questions on the proof of adjointness?
Let me just say one thing about why this is useful. I mean, we'll see later. Basically, this allows to move U on one side to D on the other side and vice versa. And I'm not sure if we'll see too many applications of that in the lectures we have, but in topological aspects of HDF, this is extremely useful because this allows you to basically say, okay, I don't know if you want to go into it, but if we had time talking about topological HDX, then you see that somehow the way of decomposing functions into the things coming from different levels of the complex, and some of the things are in the kernel of the down operator, and then somehow things cancel and behave very nicely. I don't know if we'll see many applications of that, I don't know, Max, do you remember?
We will, so we want to
Okay.
see an application of that in particular. We will see it, well, there are two very important applications we'll see of these being adjoint. The first is that when you compose them, you get a self-adjoint operator. So, without having these be adjoint, it's not at all clear that the higher order random walks even have a spectrum, or are diagonalizable. So this will immediately give us that the higher order random walks are self-adjoint. And the second is we'll actually use this to prove one of the Garland's method results that we need. So we'll see it both used explicitly in a proof, and it's important for defining higher order random walks.
Yeah.
But yeah, the thing that Shahar was talking about, we probably won't get to, but there are kind of ways to decompose functions on HDX where based on the up and down operators, and then it can be very useful to use this flipping trick. But yeah, maybe you'll see this in a project if you do Dixie Dinarfilmis and Harsha's paper, which kind of is the main paper introducing random walk expanders. You'll definitely see this used, and maybe in a few other places. Okay, so if there are, I'll pause for a couple seconds in case there are other questions. Okay, if not, so now that we have defined these down and up operators and seen a basic fact about them, that they're adjoint of each other, let's go ahead and actually define higher order random walks. So these are going to be the analogs. Actually, we talked about this last time. Kind of higher order random walks are a really big class of objects. They're not really super well defined. It's kind of any random process you can do on a simplicial complex. We'll be focusing on the three walks that we've talked about so far: the upper walk, the lower walk, and the non-lazy upper walk. But when somebody says higher order random walk, there are many other possible options. A number of papers use things called swap walks or partial swap walks. If you go kind of look at the literature, there'll be many types of higher order random walks. We'll just focus on these three that we've talked about. So let's go ahead and see the formal definition of these walks, the generalization from what we discussed on graphs. So this will be the upper and lower walks. Okay, so let's say let's x pi be a d-dimensional complex. Also, whenever I write complex, I always mean a pure weighted simplicial complex. I'm just going to write complex because I will always mean that 100% of the time. Then for 0 is less than or equal to k is less than or equal to d minus 1, the upper walk at level k, the upper walk at level k is just the composition of the down operator and the up operator. So it's just dk plus 1 uk. And so recall, just as a brief aside, kind of recall that d2u1 was the node edge node walk. So plugging in k equals 1, this is indeed kind of the generalization of the upper walk, of the node edge node walk, right? dk plus 1 uk is the walk that starts at level k, takes a step up in the diagram to level k plus 1, and then takes a step back down to level k. There's also the lower walk. So for, I guess, d is greater than or equal to k is greater than or equal to 1, the lower walk. By the way, the reason we have these constraints is that if you're at the top level of the complex, you can't walk up because there's nothing to walk to. And similarly, if you're at the bottom of the level of the complex, you can't walk down because there's nothing to walk to. So there's no lower walk at level 0, and there's no upper walk at level d. So the lower walk at level k is just the flip of this. It's uk minus 1 dk. And both of these are operators from ck to ck. They're walks on k faces. And I'll just go ahead and note that both of them are what are called self-adjoint. And why is this? So self-adjoint means that it's its own adjoint operator. So kind of when you flip it, you get the same thing. So why is this the case? Well, this is for free, right? Because D and U are adjoints. So if we first flip D, we get UKF, UKF, and then by adjointness, we get F DK plus 1 UK of F. So we get that it's always equal to putting it on the other side. This is called being self-adjoint. And the reason this is useful is there's a spectral theorem for self-adjoint operators. In particular, this means that it's diagonalizable, it has eigenvalues, it has all the, all the good stuff that we want. This is basically the generalization of kind of, being stochastic and symmetric that we had before.
Well, I mean, it's still symmetric. I mean, if you take any basis for it, being self-adjoint is the same as being symmetric.
What do you mean by symmetric? It won't be
I
transpose.
I guess
it's not
well,
true.
if you don't have F, if you had FG there, right, it would still be true.
Oh yeah, sure, but it's not symmetric because the inner product is weighted, so it's off by the weighted. You have to multiply by the weights.
Oh.
Right, IJ and JI are flipped by
right.
weights.
It's symmetric modulo the weight.
It's symmetric modulo weights, yeah. So they're not transposes. They're transposes modulo, yeah, or like U and D. Anyway, self-adjoint is up to reweighting is the same as being symmetric, but you do have to think about these weights. Well, in general, the whole reason we define this inner product, this weighted inner product, is so that you do not have to think about the weights. So you could just treat it kind of as if it were symmetric, even though it's not. That's kind of the whole deal here. We get to kind of cheat. Anyway, so this means that it has it has a spectral decomposition, has everything that we want. So we kind of don't have to worry about that sort of thing. Okay. So the first thing that I want to talk about is laziness. So recall that, recall that the node edge node walk, one second. Recall that the node edge node walk, which was equal to what? It was equal to D2 U1. This was the upper walk at level 1. On graphs, had a 1/2 lazy component. Remember, we started at a vertex, we walked up to an edge, and then there was a 1/2 chance of returning to that vertex always. So this walk was kind of 1/2 lazy. It was with, if you start at V, with probability 1/2 you stay at V, and with probability 1/2 you move to a random neighbor. And that was the node edge node walk. And the question is this still true for the upper walk in general? And if so, what's the corresponding laziness parameter of the upper walk, right? When we defined random walk expansion on graphs, we actually didn't define it with respect to the upper walk. We defined it with respect to the non-lazy upper walk. And we're going to want to do the same thing here. So we're going to want to figure out, is there laziness? And if so, how much is there, so we can kind of subtract it out, and get the non-lazy version of the upper walk. So let's, to answer this, we'll answer it very formally in a minute, but let's just look at the diagram again, because generally, if you kind of want to figure out something at least somewhat informally with respect to these higher order random walks, always go to the diagram view first before trying to chug through all of the weights to do it. Always go look at the diagram, see what you should get intuitively. So let's take a look at this diagram. So we have level xk, and we have level xk plus 1 here. And so what does the upper walk look like? Well, we'll take a step up. And remember that this step up actually corresponds to the down operator, which is a little bit weird, but because the down operator lowers functions by averaging up, the first step of the upper walk is actually given by the down operator. So the probabilities when you move up are kind of weird, but I claim that we actually don't care about them at all. So let's say we start at tau, k-phase tau. We walk up to some tau union v, but no matter what tau union v we walked up to, it's always going to contain tau, right? Tau union v, doesn't matter what v is, it always contains tau. And moreover, remember that the way that we walk down is we remove, and Shahar mentioned you can either think about this as removing a single vertex or equivalently picking a random sub k-face. So when we move back down, we'll remove a random vertex. So what's the probability that we end back at tau when we move down? So remember, moving down is nice. When we move down, we go uniformly at random. So what's the probability of returning back to tau? Well, it's exactly the probability that we remove v, right? And the probability that we remove any of the vertices is uniformly at random. There are k plus 1 of them. So the probability that we remove v and therefore end back at tau is 1 over k plus 1. Right? So probability of tau to tau, I claim, is 1 over k plus 1. Because no matter where you walk up to, you're going to, the k plus 1 phase that you end up with, by definition, will be tau union v for some v. And then when you walk down, it's uniformly at random. It doesn't depend on v. The probability of getting to tau doesn't depend on v at all. It's always just whatever the probability that you remove v is, which is 1 over k plus 1. So, just to double check, if we plug in 1 here, what do we get? We get a half. So this is indeed, correct for level 1 as well as a sanity check. So there is, in fact, I claim there is, in fact, this laziness term, and it generalizes to 1 over k plus 1 when you're at level k of the complex. Okay, maybe any questions on the upper and lower walks and kind of this laziness factor before moving on? Cool. So, okay, so now that we know there is a laziness factor, let's go ahead and define a third walk. That's going to be our analog of the adjacency matrix, the non-lazy upper walk. So definition, non-lazy upper walk. Okay, so what is this? The non-lazy upper walk at level k it's denoted by mk plus. At least I've seen this notation in a number of papers, and it's what we use in the notes. I'm actually not sure why it's called mk plus. Shahar, do you have any idea why this notation is?
One paper called MK the upper walk, and then MK plus was a non-lazy upper walk.
Yeah.
So, they don't invent the term.
All right.
MK plus.
So no good reason in particular. This is often called MK plus. I think I've seen a few places in the literature. We're also going to call it MK plus. Just to stick with the notation. So what is this? Well, all we're going to do is we're going to take the upper walk and we're going to subtract off the lazy part. So there's going to be some normalization factor on the outside that I'll explain in a second. But other than that, it's just the upper walk, dk plus 1 uk, minus the lazy term, minus the identity over k plus 1. So this is going to subtract out our 1 over k plus 1 laziness. So once we subtracted, oh, that's bad. Once we've subtracted out the laziness, we're no longer stochastic, right? The probabilities of transitioning no longer sum to 1. So it's no longer a random walk, but we can fix this by normalizing it on the outside, right? We've taken out 1 over k plus 1. So now if we don't normalize it, the weights are k over k plus 1. So we multiply by k plus 1 over k, and we end up with a random walk, a stochastic matrix. Okay, so now what we're going to do is we're actually going to go very explicitly into the non-lazy upper walk. And we're going to take a look at its transition probabilities. We're going to understand why it's a walk. We're going to understand why is it the analog of the adjacency matrix, and kind of what does it look like. So our next goal is kind of just to understand MK plus. And once we do that,
I don't know if you want to do that or not. Like, did you plan on writing a dk plus 1 uk as this convex combination of MK plus and identity? So it might be. It's equivalent to what you wrote, but it just might be easier to see why we get these terms.
Sure, we can write it that way. So you want to write.
At least for me, it's more intuitive. Yeah.
KMK plus.
No, I just been writing dk plus 1 uk.
Sure.
Equals.
So should be equal to what?
Why is that 1 over k plus 1 identity? That's a later term.
Yeah. Wait, shouldn't that get producted? No, I guess it doesn't. It doesn't. 1 over k plus 1.
Identity.
Yeah.
Plus k over k plus 1.
Yeah.
MK plus. So it basically shows that what you're doing here is a lazy component, which is identity, happening probability 1 over k plus 1. And otherwise, the probability k over k plus 1, you do something, which is going to be the non-lazy. upper walk that backs up to that.
Right.
And
So
then
this
there's
would this
combinatorial
this would be the equivalent of saying kind of node edge node, like calling back to D2U1, which was the node edge node. This was equal to what? It was equal to I over 2, the identity over 2, plus the adjacency matrix over 2. Right. So this way of defining it is kind of the analog of how we saw the lazy version of the adjacency matrix back on graphs. Yeah, I don't know. For some reason, I actually find this way more intuitive, but it's good to give both ways.
Yeah, I should have both. I find the other one more intuitive.
Yeah, just personal preference. Okay, regardless, I still do want to go through the transition probabilities of MK plus and prove that MK plus actually is the analog of the adjacency matrix. And I'm going to use this to do it. Okay, new goal. Kind of examine transition probabilities of MK plus and show its analog of adjacency matrix. Okay, so first of all, how do we actually find the transition probabilities in terms of MK plus? Well, I claim that for kind of tau and t in xk, the probability with respect to the walk that tau goes to t is given by the following form. It's MK plus 1t of tau. And you can work out exactly what this is by writing out the matrix and making sure that producting by these functions and looking at the tau index actually gives you this probability. The reason that t and tau are maybe flipped from what you would normally think is because we've talked about this a couple times, but MK plus on the right is actually the averaging, right? MK plus is a walk when you multiply on the left, and it's an averaging over functions when you multiply on the right. So the reason that this is the right form to get the transition probabilities is because it's kind of leftward defined instead of rightward defined. This isn't really something that's intuitively that easy to see. You kind of just have to write out the matrix form and see that this is indeed the right.
I mean, once you said it, I mean, if you multiply MK plus on the left by the indicator of tau, right? If you just write 1 tau transpose.
Right. Yeah. Sure.
MK plus, but that's going to give you the probability of that you get after making the step. Then you want to look on that at coordinate t, which is just this times 1t.
Right.
So, and then this you can paraphrase in different ways.
Right. Yeah. So I'm just writing this slightly differently. Yeah. Okay. Good point. Okay. So how are we going to do this? Well, MK plus is mostly just defined in terms of the upper walk, right? So to do this, it'll be enough to compute the transition probabilities of the upper walk, and then to just see what happens when we subtract off and renormalize. So to do this, we'll first examine dk plus 1 uk of 1t tau. We'll look at the transition probabilities for the upper walk, and then we'll transform that into computing the transition probabilities for the non-lazy upper walk. Okay, let's actually unravel this a little bit. So I think we talked about this a bit last time, and again, remember that. So the dk plus 1 uk is what? Well, we're on xk. There's xk plus 1. So it walks up from k to k plus 1 is the first step. And we recall that this actually corresponds to the down operator, not the up operator. We first apply the down operator to walk up a step, somewhat annoyingly. So let's first unravel this first step of the walk. Let's roll out kind of the down operator and see what we get. Well, just by definition. So here it's actually going to be a little bit easier to use the explicit definition rather than kind of the joint probability definition to unroll and actually do these calculations. So what do we get? Well, by definition, this is 1 over pi k plus 1 of x tau. There's this normalization factor. And then we have the sum over sigma containing tau, where sigma is a k plus 1 face, of what? We should have pi k plus 1 sigma times uk 1 t of sigma. Okay, so this is just writing out the definition. I haven't done anything complicated here. And now I want to examine the down step, right? So the down step corresponds to the up operator. So let's take a look at what is UK1T of sigma. And I claim that this actually has a very simple form, because 1T is the indicator function of T, right? It's 1 on T and 0 everywhere else. And what does UK do? UK just uniformly averages down over K faces included in sigma. So in particular, there are kind of two cases of interest, right? Either T lies in sigma, and in this case, there's exactly one subface that is T, which is T itself. And because you're uniformly averaging over the K plus 1 subfaces, it's 0 every time you're not T, and then it's 1 over K plus 1 when you're T. So this ends up being 1 over K plus 1. And let's say now that T does not lie in sigma. Well, when we take the average over K faces in sigma, none of them is going to be T because T doesn't lie in sigma. So every one of them is going to be 0 because you're still just applying 1T to it. There's no, it's never T. And so it has to be 0. So this ends up being very simple, right? It's either 1 over K plus 1 if T lies in sigma, or it's 0 if T doesn't lie in sigma. So basically, this observation will let us compute the transition probabilities. But to do this, we're going to need to break into kind of 3 cases of interest. In fact, really only 2 of them will be interesting. But so we're going to break into 3 cases. And it'll be dependent on the intersection size of T and tau. Sorry for the background noise. I don't know what that is. Okay, so 3 cases of interest. So case 1 is where tau is equal to T. So this is when their intersection size is K, right? They're as close as possible. This is basically the lazy term. So let's see what happens. Well, let's look at this sum, right? If tau is equal to T, then, well, in that case, every sigma contains T, right? Because by definition, sigma contains tau, and tau is equal to T. So every sigma contains T, right? And that means that UK1T sigma is always 1 over K, because T is always contained in sigma. So we can pull out the 1 over K plus 1, not 1 over K. We can pull out the 1 over K plus 1. And what we get is that in this case is equal to 1 over K plus 1 times, well, we still have this normalization factor out front, 1 over pi K plus 1 of x tau. And then the sum, what do we have? Well, we have the sum over all sigma containing tau of pi K plus 1 sigma. But remember, this term here is actually exactly what this is shorthand for. Pi K plus 1 x tau is exactly the sum of the probabilities over level K plus 1 of sigma containing tau. So these terms are equal. This term is equal to this term. And so they cancel, right? And what we get is just 1 over K plus 1. And this is kind of the very formal computational proof of this diagram that I showed you right here. That when we walk up and back down, there's always a 1 over K plus 1 probability of going from tau to tau in the upper walk. So we've now shown this, writing out all the definitions formally. We do indeed get 1 over K plus 1 as the transition probability of tau to tau. Okay, so that's case 1. Let's look at case 2. So case 2 will be that tau and T aren't equal, but they're as close as possible to being equal without being equal. So in particular, their intersection size is equal to K minus 1, right? So if it's equal to K, they have to be equal because they're K phases. So being equal to K minus 1 is the closest you can possibly be. They're basically off by 1. They're essentially neighbors. So in this case, let's take a look at what we get. Well, let's look at this again. I claim that only 1 sigma will give a non-zero interior term. And why is this? Well, T and tau are kind of 1 apart, right? And so the only sigma has to contain tau. And so the only way you can possibly also contain T is by adding in the 1 extra element that T has that tau doesn't have. Right? And so in particular, the only sigma that will contain T is tau union T. So every term that is not tau union T will not contain T and will die. So this sum basically just reduces only to the term corresponding to tau union T. So let's write that. So again, we'll end up getting a 1 over k plus 1 from the up operator applied inside. We'll still have this normalization term, pi k plus 1 of x tau. And then in this entire sum, the only thing that survives is tau union t. So what do we get in the sum? I've already pulled out the 1 over k plus 1, but the main probability is pi k plus 1 of tau union t. So maybe writing this a little bit more nicely, 1 over k plus 1, pi k plus 1 of tau union t divided by the link probability, pi k plus 1 of x tau. So this should maybe already ring a bell with respect to the adjacency matrix. We're not quite there, but it should look somewhat familiar. And I'll say exactly what I mean by this in just a minute when we subtract out the lazy term. So case 3 is not actually interesting, but we have to talk about it. So tau union t is less than k minus 1. So this is when tau and t are kind of more than 2 apart from each other. Like t has 2 elements that don't lie in tau. And I claim that this is very obviously 0. And the reason is that if t is more than 2 elements away from tau, in sigma, what we're doing here is we're adding 1 new element, right? So if we have to add 2 new elements to get to t, we're clearly never going to get to something that contains t, 2 or more new elements. By adding 1 element, we can never get to t, right? So this inner sum will always be 0. And this is the same, again, you can just see this on the diagram, right? If you walk 1 step up and 1 step down, you only ever introduce 1 new thing. You can't possibly get to a k-face that's more than 1 thing away by adding 1 new thing. So it's going to be 0. So in case 3, we get that the transition probabilities are 0. So there are kind of only actually 2 cases of interest for the upper walk. There's the lazy term with 1 over k plus 1. And then there's this term of kind of neighboring tau and t that are 1 away. And you get this kind of transition probability that I'll discuss more in a bit for MK plus. Okay, any questions on these calculations before we port them over to MK plus, which was our original goal? Okay, if not, let's go ahead and see what this means for MK plus. So recall that MK plus is equal to k plus 1 over k dk plus 1 uk minus identity over k plus 1. So let's see what this means for the transition probabilities. Well, in case 1, we have what? So we're going to get, in case 1, this is tau equals t. So in this case, we're going to get a 1 over k plus 1 contribution from the upper walk. And then we have the identity here. So we're going to get a minus 1 over k plus 1 contribution from the identity. And this is 0, right? Doesn't, we can normalize 0 all we want. It's still going to be 0. So we end up getting a 0 transition probability for the laziness term. So we do indeed see formally MK plus is non-lazy. So we get case 1, we get 0. I'm just going to go ahead and skip case 2 because that's the interesting case. I'll come back to it. So in case 3, we have tau intersect t is less than k minus 1. And in this case, we have this term is 0, and this corresponds to an off diagonal of the identity. So this is 0 as well, and so we get 0 minus 0, and this is still 0. So case 1 and case 3 are now both 0 transition probability. The only time we have a non-negative transition probability is between neighboring tau and t that only differ in 1 element. So finally, we reach the interesting case, case 2. And here we have tau intersect t is equal to k minus 1. And in this case, there's still 0 contribution from the identity, right? Because this is an off-diagonal term. Tau is not equal to t, so it's off the diagonal. It has 0 from the identity. So all you get is this normalized version of the up operator term. So just, before we had 1 over k plus 1, now it's just going to turn into 1 over k. So what do we get? We get that the transition probability looks like the following. 1 over k, pi k plus 1 of tau union t divided by pi k plus 1 of the normalization for the link of tau, pi k plus 1 x tau. Okay. And I claim that this is actually a natural analog of the adjacency matrix. Why is that the case? Well, let's just plug in k equals 1 and see what happens. So first of all, this normalization term dies, right? 1 over 1 becomes 1. Let's let tau equal v and t equal w, because we're on k equals 1. So they're just vertices. So what do we get? Well, we get pi 2. So we get the edge weight of VW. So the transition probability from V to W is what? It's the edge weight of VW divided by the total weight around the vertex V, right? What is pi 2 of xv? It's just the sum over the neighborhood over maybe, let's say, W prime in the neighborhood of V of pi 2 of VW prime. And this is exactly how we define the weighted adjacency matrix, right? This is the natural random walk underlying a weighted graph. So when we look at k equals 1, this does indeed reduce to the adjacency matrix. That was exactly what we were hoping for, right? We wanted the non-lazy upper walk to be some sort of generalization, level k generalization of the adjacency matrix. So we've at least seen that when we reduce to k equals 1, we get back the adjacency matrix. So that's a good first step. And I also claim that this is just a fairly natural object, right? Because so you can think of kind of 1 over k times this pi k plus 1 x tau. This is just a normalization factor, right? It's you have to normalize by something to make sure that the transition probabilities add up to 1. But basically what we're saying is that the transition probability from t to tau, from tau to t, is just proportional to the edge weight between tau and t. Right, that's morally what this pi k plus 1 tau union t is saying. It's saying here's the edge weight between the neighboring k faces tau and t. We're going to move with probability proportional to that edge weight. Right, this lower part is just a normalization factor. You can more or less ignore it. It's the appropriate thing to make sure we're a random walk. But all you're doing is you're moving proportional to the edge weight. It's exactly the same thing as you're doing here, where you move proportional to the edge weight. So I claim it's kind of the, or at least a, natural generalization of the adjacency matrix, or of the kind of non-lazy walk on a standard graph. Okay, so that was maybe a lot of material to take in. So I'll pause again. Are there any questions about kind of how this generalizes the adjacency matrix, or how we computed the transition probabilities, anything we've covered so far? Or comments from Shahar?
One comment. Here's the way I'm thinking about it. So you can think of it as, how do I go from tau to t? So you have tau. You go up to a k plus 1 phase. And that has this probability of pi k plus 1 of tau unit t divided by pi k plus 1 of x tau. So you go up to a k plus 1 phase. And then you want to go back down to a k phase. But in general, you have k plus 1 options, but you're ruling out the lazy option. So you cannot just go back. You have to go back to a different k phase, and you have k options, which is why you have this 1 over k normalization factor. But after you went up to a k plus 1 phase, and you ruled out just being able to go back, you have k new options to go to. So that's another way of interpreting this term.
Yeah, that's a nice way of seeing why this equation is how it is as well. Yeah, so this term here basically corresponds to the up step, where we're taking kind of probabilities proportional to moving up, and then down, instead of having k plus 1 options uniformly, you have 1 over k, like Shahar was saying, and so then you get this term. Yeah, that's a nice way to interpret it. Okay, we have 12 minutes. All right, we'll see how much of this we can get through. Okay, so now that we've defined and kind of looked at MK plus, we're actually finally ready to define random walk expanders, to define the generalization of kind of a random walk version of two-sided spectral expansion on graphs to simplicial complexes. So let's go ahead and do this. Random walk expander. Okay, so we say a d-dimensional complex x pi is a gamma random walk expander if for all 0 less than k less than d. And note that for graphs, which are d equals 2, this is just k equal to 1. The non-lazy upper walk, the spectral norm of the non-lazy upper walk
minus the lower walk is less than or equal to gamma. So for all levels, you want this connection between the non-lazy upper walk and the lower walk to hold. So this is clearly a direct generalization, right? Because we saw up here that M1 plus is equal to the adjacency matrix on graphs. So if we just plug in D equals 2, this becomes A minus, 1 over N J. We get back our initial definition on graphs. So this is a generalization. But just kind of looking at it, it's not really super clear how to think about this, what it really means for the non-lazy upper walk on level K to be the same as the lower walk. It's not quite as obvious whether this has a strong spectral interpretation. In fact, it does actually say something about the eigenvalues of the walks, but that's something we'll cover in sampling applications. But not quite the same equivalence that you get for graphs. So I want to talk about kind of one way of viewing what this means. It's actually not really a way that we're going to make use of in the rest of the course, but I do think it's a kind of natural way to view these things, and they are useful in other contexts. Maybe you'll see it in the final project or something like that. But so one way to think about what's going on here is to consider the case of gamma is equal to 0. And I want to actually note, kind of as an exercise in definitions, and the proof of this is like one sentence. You just kind of have to make sure you understand the definition. I claim that no finite complex is a 0 random walk expander. So this is going to be useful morally to understand what's going on, but as a finite object, it actually does not exist. And this is pretty much immediate from the definitions. I'll leave it to you to think about because I think it's useful to think through the definitions to understand why this is true. But so this is not actually an object that exists except in kind of infinite limits, but it's useful to think about regardless. So what does it mean if gamma is equal to 0? Well, this implies that that MK plus is actually equal to, that the non-lazy upper walk is actually equal to the lower walk, right? Because if they're not equal, then you have a non-zero, the spectral norm of a non-zero matrix, and the spectral norm of a non-zero matrix always has a non-trivial eigenvalue, always has a non-zero eigenvalue. And so you get you would get gamma greater than 0. So if it's equal to 0, these matrices actually have to be equal. These operators have to be equal. And writing out MK plus, what does this mean? Well, this is K plus 1 over K of the upper walk dk plus 1 UK minus the identity over K plus 1 is equal to UK minus 1 dk. And what I want to point out is that there is kind of some interesting statements here that's being made. And it's that kind of up to this laziness factor, kind of ignoring this laziness factor, the down and up operators commute, right? So we say that operators A and B commute if AB is equal to BA. And this is in general something that doesn't happen that often when you're working with operators, right? So with matrices, for instance, it's kind of rare that matrices A and B would commute, that AB would be the same as BA. And indeed, it's not quite true down here. There's this laziness factor that comes out when you flip them. But kind of up to laziness, you can commute the down and the up operators. And this is one way to, sorry?
And also there are different operators, right? I mean, you have UK and DK plus 1 on the left, and you have UK minus 1 and DK on the right.
Right.
So they commute up to being different operators.
Yeah. They commute also up to level. Yeah, so they commute up to both level and identity. But again, kind of because of how we've defined the joint distribution and the down and up operators, you kind of for free get to ignore the fact that you're moving between these different spaces because of how we've kind of magically defined all these things in a way that's really nice. So yes, Shahar's right. Up to shifting one level and a laziness factor, the operators commute. You can kind of you get to flip the operators for free, except for this additional laziness factor. And the idea, one way to think about random walk expanders is that this is approximately true in a spectral sense. That kind of you can flip U and D up to this laziness factor, and you'll only lose something small with small spectral norm. So when would this be useful? Unfortunately, we probably won't see this in this course. But if you go, read more literature, again, if you look at So actually, I should say, sorry, this is from a paper of Dickstein, Donner, Filmus, and Harsha. Oh, yeah, let me actually give some attribution earlier as well that I forgot. The walks are originally due to Kaufman and Mass 5 years ago in 2016. The random walk expanders are slightly more recent from Dickstein, Donner, Filmus, and Harsha. Anyway, so if you go, for instance, and you actually look at this paper, which is a great paper, you will absolutely see this view where kind of, they think about it as these down and up operators commute up to a laziness factor plus some, they approximately commute up to some factor. And why is this useful? Well, essentially, whenever you're kind of working in some kind of L2 space, whenever you're working in an inner product or something like that, the idea is that up to this laziness factor, you get to flip D and U for free, right? Because essentially what happens is you flip D and U, and what you end up with is okay, so there's some lazy term that kind of racks up, but this is necessary. And then there's some error term that comes from the gamma, right? There's basically some difference that ends up having small spectral norms, that has gamma spectral norms. And then because you're working over kind of an L2 space, because you're working over an inner product, you can basically bound all of the error terms by gamma. And so what you get is kind of the flipped version plus the laziness plus some error term. And you can use this to prove a number of very useful things that you can see in Dickstein, Donner, Filmus, and Harsha's work, or this is used, I think, also in kind of works on approximation algorithms for constraint satisfaction problems. It's been used at least implicitly in actually error correction in efficient list decoding, I think. So it's come up in a lot of places, none of which we have time to cover, unfortunately. But if you go look at the literature yourself, or maybe in final projects, you might come across this viewpoint of random walk expanders. Okay, so my plan was to go through actually an example of a random walk expander, and maybe I'll just give the claim and give the proof on Tuesday because we have 4 minutes, and I don't really want to rush through it. So what's the first thing that we always want to check when we define a new definition of expansion? Well, we better check that the complete object is expanding, right? So in this case, we want to check that the complete complex is actually an expander, just like I believe we checked that the complete graph was a spectral expander, we checked it was a vertex expander, we checked it was an edge expander, we checked that the complete complex was a local spectral expander. Now we're going to check that the complete complex is a random walk expander, or we'll check it on Tuesday, but I guess I'll claim it for now. So claim to be proved on Tuesday, mostly in class. I claim that, so J and D, I don't know if we've used this notation yet, but it's very common. So the complete complex on n vertices and d dimensions, this is every possible d subset of n. This is either called the complete complex or the Johnson complex. I think Shahar mentioned this. For historical reasons, it's called the Johnson complex. I think just because Johnson worked on it in coding theory and the name kind of caught on. So often you'll hear Johnson complex. People won't tell you it's a complete complex, but now you know. If anyone says Johnson complex, they mean the complete complex. So I claim that J and D endowed with a uniform distribution across top level faces, so everything is really symmetric, right, in this complex. I claim that this is I think it's a 2 over n minus d random walk expander. So basically, as long as d is significantly less than n over 2, then this is, as n goes to infinity, gamma here goes to 0. It's a really, really, really good random walk expander, as we would hope for any definition of expansion, right? Because at the end of the day, what we're trying to define usually is some kind of robust notion of connectivity or things mixing, and then the best possible version of this is always the complete complex, complete graph, etc. So for a definition to make sense, we better hope that the complete complex is a really good version of it, which it is here. With 1 minute left, okay, let me maybe just make another observation that has to do with kind of this commuting viewpoint. And it turns out, we won't prove this in this class, but it turns out that if you allow these constants on the outside to change, if you allow this to kind of be alpha and you allow this to be beta, you actually can get perfect random walk expanders. In particular, the complete complex does actually satisfy this U and D commute up to laziness. It won't quite be 1 over k plus 1. There'll be some like 1 over n error terms in there. But these are called sequentially differential posets or sequentially differential complexes. They were introduced by Richard Stanley, like 50 years ago at this point. And it's kind of interesting that they've, within the last 3 years or so, they seem to have these connections with high-dimensional expansion and are coming back to be of interest. There are other objects that are really interesting that also satisfy this, like the Grossman poset, which is kind of something similar to like the flag complex that you've been working on in your homework. It's like the vector space analog of the complete complex. But anyway, so this is to say zero random walk expanders don't exist. But if you extend the definition a little bit and kind of allow coefficients to be a little bit different, you can actually get this D and U commute behavior perfectly. These objects do exist. The complete complex is an example of it. I think in the notes we give the exact parameters for the complete complex. So if you're curious, you can go check it out in the notes. Anyway, we've hit 12:20, so I'll stick around for a few minutes for questions, but otherwise I think we're done for today. We'll pick up on Tuesday with the example of the complete complex and then proving our main theorem for the section, equating random walk expanders to local spectral expanders.
Maybe like one comment about the general difference between random walk expanders and local spectral expanders. So local spectral, like the name suggests, are local, right? We look on every link in this complex and we say something about it. And we say, well, maybe it's enough to look at top level links, but still on every link. And this random walk expander are more like a global definition. It asks what, if you have these random walks on the complex, how do they behave? Do they mix fast and so on? So they don't do on every link. So if one link is bad, this might not notice it. But globally the graph is okay. But so maybe surprisingly, even though this is a global object, you cannot have a few bad links. I mean, this notion is something equivalent to a local spectral expander. And to me, that's a very surprising fact. It's like saying you have a graph, it's almost an expander, but you took like one vertex and somehow remove it away, right? Or you messed it up, right? So globally, this random option sort of almost look like it's mixing, but it's not quite mixing. You can actually sense that on this one vertex that you messed up. And the same phenomenon sort of happens here. Anyway, to me, that's surprising.
Yeah, I think it's surprising as well. We'll see on Tuesday. We'll see one direction of the proof. We'll see the local to global version that proves that local spectral expanders are random walk expanders. For the converse, which is actually, I think, the surprising part that Shahar was talking about, we won't have time to cover it, so you'll have to look at the original paper, which is pretty well written. So I think it's worth looking at. All right, so stick around for a few minutes if there are questions, but otherwise I think we're done for today.
Yes,